I would like to welcome an expert in today's topic, which is intelligent completions, particularly as it relates to deep offshore. And you have read his biography, but I'm just going to pick on one part of it, which says, you know, he's been doing this since 1994. So that's 28 years, getting on to 30 years. And he worked on the deep water subsea projects in the Gulf of Mexico, West Africa, North Sea, and the Mediterranean. I was just asking him, you know, where in the Mediterranean, and he says deep offshore Israel and Egypt, and also Libya. He's got experience in those areas. And then, you know, I have to definitely touch on his last paragraph in his bio. He has 3 children who are all engineers. So he is, I have two children, one is an engineer, so he's ahead of me. With that, it is our pleasure to welcome Ron, and I will hand it over to Ron. Oh, before I said I hand it over to Ron, I also wanted to mention this paper here that may be of interest to you. He just presented this paper in the annual technical conference of SBE a couple of months ago in Houston. If you are interested, he presented this paper. Go and look it up. And he also tells me that he mentors some other students and likes sharing his experience with the general community. So let me stop sharing, and I will hand it over to Ron. Please.
All righty, thank you, Gökhan. That was, you know, thank you. And I'll go ahead and I'll get this started here with the. Hopefully start seeing my screen, and I'll put this into presentation mode. And alrighty, can you see my presentation now, folks?
Not quite.
Okay. There we go.
You
should see it now.
Yeah. Now
okay, good. Now we got it. Alrighty. Let's go ahead and I'll pull this up as well, and hopefully I can make this. There we go. Okay. Again, good evening, everybody, and Gökhan, good morning over in Calgary, and thank you everyone for joining us today. I've got this presentation. It's an introduction to intelligent completions, and on that, I will get going. And if I can find how to, here we go. What's going on here with this? It seems to be frozen.
Yeah, if you want to get out of the presentation mode, then that one was a good size too.
Yeah, it's kind of funny because it was just working for us just a moment ago, and now it is not. That's amazing how that works.
Try the down arrow.
Yeah. Can I go back to this? There we go. That'll work too. Thank you. Right. Our just the objectives in today's discussion is again, it's an information share. It's meant to be informal. I think we'll save the questions to the end, just that way, just to maintain the rhythm, make sure we finish up on time. The topics today, I'm going to kind of go over just the definition of an intelligent completion to be sure we're all on the same page. I'm going to talk about sensor design and reliability, ICV designs, on-off and choking electric. Look at some intelligent completion configurations and also some design considerations and lessons learned from past projects. What is an intelligent completion? Like in a normal well, an intelligent completion has got downhole sensors that provide you real-time temperature measure, temperature and pressure data. These are usually our electronic gauges, quartz gauges that we've been running in the fields for many, many years. However, these days there are many installations that have fiber optic and other data sources. We're starting to see distributed acoustic sensing being run in subsea completions, although that's still fairly new. What makes an intelligent completion intelligent, though, is that in addition to those sensors, we run these surface-controlled interval control valves, or ICVs, that allow us to control flow into or from 2 or more reservoirs. So you've got sensors that provide the data, and then you have the ICV, the smart valve that gives us the ability to act on that data without having to intervene on the well to improve the flow characteristics of the well. And one thing I will say too, I know I'm presenting in English, and that's, for you folks, it's a second language. So if I'm speaking too quickly, please don't hesitate to jump in and let me know. I'm going to run through here just a few items that you'll see in an intelligent completion as far as completion components. We have our tubing encapsulated conductor or fiber that communicates between the gauges and surface. We have our downhole sensors. I'll talk more about those in a little bit. In some cases, we have new flow paths. This is a 2-zone intelligent completion. The lower zone flows as we'd expect. It kind of comes in from the perforations and through the screens, then up through the tubing on the ID. The upper zone, because in this configuration here, the intelligent valves are higher in the well, it enters through the screens and it flows through the annulus alongside the casing for quite a while before it enters the well. And so in these kind of configurations, you may want to consider changing your casing metallurgy because it's at the same risk of corrosion as your tubing would be. We have the hydraulic lines for the intelligent control valves or interval control valves. And to get those lines down to the valves themselves, and also to get the cabling for your sensors down, you have what we call a feed-through production packer. These are often very similar to the conventional packers, but there are penetrations through here for control lines. We have our 2 ICVs. I'll touch more on these in a little while. And we also have what we refer to as a telescoping space-out joint. This is in most of the completion types. That is basically used to provide some tolerance for our space out because we'll be stabbing these seals in here at the same time we're landing a tubing hanger up above, and that gives us some tolerance for errors on our tallies. I'm going to jump in here and talk a little bit about downhole electronics. I'm focusing on gauges, but this also has implication for all electronics that you run downhole. And the biggest thing is that they're not alike, and you do not want to treat these as like a commodity item. You really do want to focus on the quality and really understand the product. Excuse me. There are several generations of electronics that are out there. The older ones are the printed circuit boards that later on evolved into ceramic hybrid. Some of these are what we refer to as silicon on insulator. And the more modern constructions are application-specific integrated circuits and multi-chip modules. The PCBs go back to the 1990s. These are older gauges. They are not terribly reliable in downhole conditions. They don't like vibration, they don't like shock, they're sensitive to temperature. Lots had issues where as they got warm, gases came out of the electronics that were corrosive and damaged the gauges. And they also had a lot of capacitor failures, but they're still out there as low-cost offering. And I'll note that the accuracy and resolution of these gauges, the output that you get, could be just as good as a modern gauge, but they just don't last as long. After the PCBs came out, we had ceramic hybrids. They're a big improvement, and they'll work in a lot of wells these days. Then we have the more modern, what I refer to as a premium gauge. I won't dwell on this page too long, but there is an industry standard out there, this AWS RP3362, that you can use to evaluate electronics reliability. And again, this is purely the electronics package. It doesn't look at cabling or connectors or any other aspect of the gauge. It's just the electronics. It'll allow you to assess how long those electronics can last in your well at your operating temperatures. It's based off of fundamental chemistry, because the aging process in a gauge, up to the point at which you damage the gauge permanently, the aging process is a chemical reaction that is driven by temperature. And there is like what we refer to as a 2x10 rule, where for every 10 degrees Celsius drop in operating temperature, you can double the life of the electronics. And what this really boils down to is this plot here. What I've taken here are reliability data from 5 different gauges of 4 different construction types. And I've taken their oven testing results, which is a statistical analysis, and plotted up here on a chart. If I start here at the bottom, there's the older printed circuit board gauges. If I ran these at 150 degrees Celsius for a year, I have about an 80% chance, 80% reliability with 80% confidence that those gauges are still working. If I change that out to a ceramic hybrid gauge, so the same operating temperature but different gauge construction, I'm approaching about 8 years, so almost an order of magnitude improvement in reliability. And then if I go to one of the ASIC constructions, which is the application-specific integrated circuit, I'm probably approaching about 50 years here. So I've had over an order of magnitude improvement in reliability by changing these gauge constructions. And then likewise, if I take this gauge and run it 175 Fahrenheit, I'm back down to 10 years. And that's not long enough for what we typically see as a deep water development in a hot field. But there are other gauge constructions that are suitable for those temperatures for, in some cases, potentially hundreds of years. And so, what we're kind of seeing here is that, again, not all gauges are alike. Differences in construction, which are not evident based on reliability or other kind of parameters, but differences in construction and testing can give you orders of magnitude differences in reliability downhole. And so, again, when you start looking at downhole electronics, you really want to go through and you want to assess reliability using a methodology like is described in AWIS, or another one that you may be satisfied with, but definitely challenge the reliability claims that come from the vendors. What this means in our wells, basically, the modern gauges, I didn't touch on it, but cable splicing systems are the same. They're much superior to the systems that we were running just a few years ago, and they've improved to the point where the cabling and the connectors and the things other than the downhole electronics are now our biggest problem for reliability. And so, and what that can also mean is that maybe you need less focus on electronics reliability, and maybe we get rid of redundancy, and in doing that, reduce the number of connectors in the system and actually improve the reliability that way. Fiber has a lot of promise for more and better data, but the optical connections between the tree and the tubing hanger are still in their infancy. Fiber is being run right now in Ghana and in the US Gulf of Mexico, and the run history has not been perfect. Okay, going back and thinking more about the sensors here, we have several places we can place sensors. I like to run sensors above the production packer, both on the tubing and on the annulus. The one on the tubing side can help give me rate and fluid density data, and the one on the annulus is really important for integrity monitoring. And then we typically will run pressure sensors for each of the ICVs. We'll run one on the outside, so it's reading on the reservoir side of the ICV. So if the ICV is closed, we can still get reservoir data. So if you want to do a pressure buildup analysis or similar, you can get that data. We run one on the tubing side of the same valve, and that way we can measure the differential pressure across the valve as well as flowing, so we can calculate our rate and assign volumes to that interval. I touched now on the hydraulic ICVs. Again, I'll go through a few designs, but the hydraulic ICVs are definitely the workhorse of the industry. The vast majority of what's been run out there are hydraulic ICVs. They're very similar to slickline sliding sleeves. In fact, I think they evolved in many cases from slickline sleeves. The key difference being that there's a piston on the insert. So you have the body of the valve here in yellow, that this doesn't move. This is what's screwed into the tubing. This bit here in the orange is what floats up and down, and to turn the valve on and off. And with this valve here, if I pump in the bottom line, which is the closed line, the open line, and it pumps this piston up and it opens the valve. And conversely, if I pump in the closed line on top, it'll pump the piston down, it'll close the valve. There are two basic constructions. One is the annulus to tubing ICV, which, as the name implies, it flows from the annulus into the inside of the valve. Again, the vast majority of valves are of this construction. This would be the upper of the two zones that we were just looking at in one of the previous drawings. Or if you were to run these across a lower completion, as I think you folks are looking to do, because I think you want to run more than two ICVs, they'll generally be of this construction. The other one we have is a tubing to tubing ICV, and you'll notice the valve itself is the exact same valve, but onto it we've mounted this pressure containing shroud with a ported sub and a diverter plug. And what happens here is a flow comes up the tubing, enters this pressurized shroud, and then enters the valve. And so it's just they're using the shroud to divert the flow around. And if you needed to do a deeper intervention, you can remove this plug, in most cases and reset it later on after the intervention. So you still have vertical access to the well. What I'm showing here are on-off valves. They'll stroke from full open to full close with a pressure pulse. There's nothing limiting their movement. But we also have what we refer to as choking ICVs. And I apologize, this drawing here, this is supposed to be the same valve, even though it's drawn differently. This valve is unchanged. What we can either do is either have a hydraulic limiter, which is what we have here, which limits the amount of fluid that goes to the ICV on every step, or you can do it with mechanical, like a lug system inside the valve. And what this basically does is, rather than the valve fully opening, when you apply pressure from your control system, it'll open in very small increments. And because the flow area is less than full open, there's less flow area, and there's therefore more pressure drop across the valve, and it chokes the flow across the valve. I'll note that these choking mechanisms, they add a lot of cost and complexity, and with complexity comes risk. They're more sensitive to fluid control fluid contamination. And also there's a reset that needs to be done. I'll touch more on this in a moment, that if the well cannot get back to that reset condition, you won't be able to open the valve any further. And so it's possible to get stuck in a highly choking, production limiting position and be unable to reset the valve beyond that. And I've unfortunately had the experience with several clients trying to sort out valves that've got those kind of problems. And so it's for that reason that my recommendation is that if you're looking at these type of valves, always start with an on-off valve as your first choice. And if your production teams and reservoir teams, everyone can kind of get together and look at the value of choking and then agree that there is a lot of value in choking that offsets the risk, by all means run them, and people do run choking valves successfully. But I would never recommend that you run a choking valve just in case it adds value later. If you don't see a clear value in it, always go with an on-off valve. And yeah, so I've got an example here of a choking system. This is from one vendor, and it's again a hydraulic choking system. They're all unique, but they also share a lot of similarities. So other choking systems will behave in a similar way. You've got a closed line that's tapped in directly to the valve, and an open line that comes across two pistons. One's a very large piston with a large swept area, but no spring. The other one here is a smaller piston with a much smaller swept area, and it has a spring on it. And so if I want to go ahead and open the valve initially, I apply pressure on the open line. It pumps this piston down, and it moves the insert up quite a ways. And then the second piston comes in, and we've just cracked the valve open. We're about 2% open, so we're flowing, but with a lot of pressure differential across the valve. If I then bleed the pressure off the open line, the spring will reset this piston, but this one here has no spring, so it won't move. And we go ahead and we let this reset. This reset process usually takes about 30 minutes. And again, just considering design or conditions that have to be met, this open line here has got to bleed off fully, because this is a very weak spring. If I can't bleed all the pressure off, the spring won't reset. There are also very, very tight tolerances in here. Like they're just a few 10,000ths of an inch between metal surfaces. And if there's debris in here, this could get stuck and also prevent it from resetting. But if it does reset, we come back to this position here. I can go ahead and reapply the pressure, and I move open like another 2%, bleed the pressure off, and it resets. Another 20 minutes or 30 minutes goes by. I can do this again. And this isn't like 50 valves or 50 steps to open. Very quickly here, the flow areas are going to increase a lot more. And most of these valves will be fully open in about 12 steps. I can go ahead and bleed the pressure off. Now, if I want to close the valve, I can apply pressure on the closed line. I'll pump the insert down, and the fluid will come back out through the open line. So it's going to push this big piston back up to where it started from, and any excess fluid will pass these check valves here and also exit out the open line. And so my choking valve is fully reset. Again, this is one vendor's design. Others that have choking capability work in similar fashion. Right, now we want to start talking. I was going to talk about some alternative designs of ICVs. One that's fairly new, I think there's 4 in the ground right now, and all the vendors well, most of the vendors are working on this design, is basically taking, instead of that stepping module we were just looking at here, taking an electrically driven downhole pump and using that to open and close the ICV. So the valve itself is exactly the same. So this is a field-proven valve, and maybe hundreds of these in the ground. And what we're doing is we're adding this module up on top of it. There are some offerings out here. Metrol and I think Halliburton have got one that has it's a battery operated system. But I think the most of the focus is on using a cable, like attaching it to the TEC, the tubing encapsulated conductor that operates the downhole gauges. Although the current draw amount of power this consumes means you cannot use a monoconductor or a conventional TEC. So you're having to use a twisted pair, and that can have implications to your subsea tree because it's a different wet mate you require in the subsea tree, but it can be done. And one thing I'm not showing here is that there's also a lot of complexity in the system for pressure compensation and just how you get electronics and hydraulics packaged and run subsea. It's a lot more complex than the drawing shows. Just very quickly talk about some benefits, pros and cons. Some key benefits is you're eliminating the control lines as a leak path, and I'll touch more on that later. You're getting rid of the thermal gains in the control lines, which I'll touch on, again, in more detail later. A very important aspect of this, I think, is be meaningful for TPAO is that you can run more than 2 or 3 ICVs in a well. Talking to some of the vendors, they can run up to 10 ICVs on a single TEC using this technology, and also choking. I mean, once you've installed this pump down here, the choking functionality is basically built into the system. This does come with concerns, though. I mean, we were just talking a little bit ago about the electronics construction and reliability. This is full of electronics, and reliability under those downhole conditions is just as important. This technology is not yet field proven. There are, I think, 4 of these valves in the ground in Norway, and they've not been in the ground for very long. So, I mean, we don't know how they're going to perform in 10 years. There is tremendous complexity, obviously, in this pumping package. And a concern I've got is around the TEC reliability, or actually more critically, around the connection interface between the subsea tree and the tubing hanger. Those have not typically been very reliable. Thinking of Equinor, for one, they've had about a 25% failure rate of their connections for their downhole gauges. And so if your TEC were to fail, you would lose the ability to operate this ICV. Another designs out there are what I refer to, at least anyway, as a downhole piloted ICV. So basically, we can run either two cables, or in some cases 4 or 5 hydraulic lines, and on each set of valves we have basically these pilot valves, and you either using like a TEC to shuttle these valves, or using hydraulic logic, similar to what we do like on production platforms, where which lines are pressurized. There's a logic to that then assigns positions these shuttle valves. You can then line up some shuttle valves to allow a valve to be operated while the other ones are still blanked off and left in their static position. I know this logic has been used in a few fields around the world. I think in parts of Asia, and also one field I can think of in Africa. The big benefit of this is the obvious one, is that you're reducing the number of control lines. If you're needing to, if you want to run more than 2 or 3 ICVs in a subsea completion, this is another way of doing it. It comes with concerns. I mean, you have a lot of complexity once again, whether it's electronic or hydraulic operations. And another thing as well is if you have any leakage across these pilot valves, which can happen, you can get uncommanded valve movement from that as well. But I know like Halliburton have got they refer to this as their DigiX system, and they've got a few of these in the ground, and I think they've worked quite well. Another one that's out there is what we refer to as a side pocket, all electric ICV. I think there's several companies that offer this type of technology. And basically what you have is a plug type choke that's attached to a little motor here. And so as the motor spins, it raises and lowers the choke stem, and the flow comes in, again, through the side pocket, past this choke, and then into the main tubing string. And if you want to, you can actually put gauges in here, because this is like a venturi of a sort, and you can actually use this to allocate volume and even production type at each ICV, which is pretty slick. It's an all-electric system. You can run a number of ICVs. far more than you can do with conventional hydraulics. And again, you've got rid of the hydraulic lines in their entirety, which, there's a lot of benefit in that. There are concerns, though. We talked a lot again just earlier about the concerns of the electrohydraulic systems. This is very similar. You've got, you're relying entirely on your TEC, and this is less proven technology. Another thing about this is that this is an eccentric design. So for a given running OD, and we're always pressed for diameter, you're limited to a much smaller tubing through the middle, and that tubing reduces your small ID and more risk of erosion. So this is a less rate capable valve than some of the other designs. Excuse me. So I was going to talk here about these, different intelligent completion configurations. Over here on the left is basically the Gulf of Mexico standard. I know TPAO were asking about Gulf of Mexico completions that have perhaps run more than 2 ICVs. And I actually reached out to Halliburton, all the suppliers in the U.S. Gulf, and nobody has run more than 2 ICVs in a Gulf of Mexico intelligent completion. They're all of this design right here. Not saying it can't be done, but just in the Gulf, they've chosen not to do that yet. Having said that, there are really good examples elsewhere in the world where they've run, many ICVs in a completion. There's, North Sea, I think Johan Sverdrup, I think right now with Equinor, they're running a design similar to this one over here on the right that has no sand control, but they're running, strings of ICVs as part of the upper completion. There's the 10 field in Ghana that Tello operates is similar. BP, it's BP in Azerbaijan. They've got similar completions, and there's others in Southeast Asia. The vast majority of completions that have got more than say 3 or 4 ICVs have been run in wells without sand control. It is possible to do one inside of a sand control completion, and I'll touch on this because I'm pretty certain that your Sakarya field is going to require sand control. Just when I can interpret from well depths, and you just think of analog fields, and so you'll be looking at a similar system to this where it is run inside a sand control completion. I think I'll just but obviously in terms of being able to run a multi-zone completion, if you have a number of reservoirs, obviously running 1 ICV per reservoir gives you much better control of your reservoirs. Trying to optimize production from 5 reservoirs with 2 ICVs is obviously not in any way optimal. In fact, I'm actually working on a field right now offshore Mexico where we essentially have 4 reservoirs. We're having to bundle 3 of them together into one to be able to operate it with 2 ICVs. The challenge of this type of completion is how one of the biggest ones is how you control this many ICVs. On subsea completions, we're limited on the number of lines we can run through the tree system, and even having all those lines on the production tubing is impractical. And so you're kind of forced into an alternative design like an all electric or piloted or some of the ones we were just touching on. And again, field proven technology is what we're always striving for in deep water, and all those technologies are not yet field proven. And there's a lot of complexity here. I mean, you have, just for example, we were talking about the impact and the risk associated with splices on gauge systems. And all through here, there are many more splices on this system here, all of which are going to detract from our reliability. And also just, I have a slide here is kind of focusing on just, doing a multi-zone, intelligent completion like this with 4 or more ICVs inside of a sand control completion. There are some additional concerns, and I did work on a design just like this for an operator in the U.S. Gulf some years ago. And after we risk assessed it, we chose not to run it. But one of the big ones is fitting your ICVs inside the screen assemblies. Most common sand control we use in deep water is inside of an 8.5-inch hole. So it could be an 8.5-inch open hole, like for horizontals, or 8.5-inch ID on the casing. And most sand control systems that work inside that casing size have got about a 4 3/4-inch minimum ID. And inside that ID, about the largest ICV you can fit in there is a 2 7/8 nominal ICV. That's not a big valve. It's going to have rate limits. Another consideration as well is that's not a commonly run valve. They're out there, but they're not nearly as common as 3.5 and 4.5. And so a lot of the alternate designs like the electrics may not yet exist in that size. There is one vendor I know of, and possibly more, that has a 6-inch ID a single trip multi-zone screen assembly, and that would be suitable for a 3.5-inch ICV, and that's actually a design we worked up for that client in the Gulf of Mexico. But one downside about that is the gap between the screen OD and the casing ID is really tight, and that can have impact your annular pack integrity. And so just, you may be risking your sand control to fit a bigger valve in there. The other question is, how do you actually get the ICVs across the reservoir? It might be possible to integrate the ICVs into the screen assemblies, and Exxon are actually planning to do that in Guyana, I think in 2024. But this requires a downhole wet mate to be able to operate the ICV when you run the upper completion. And those downhole wet mates are still very much in their infancy, at least ones that could convey enough power to operate a system like this. I know there are some proven wet mates out there, but they're not compatible with this system. You can run the ICVs as part of the upper completion, which is what we were proposing to do. That's what this is. There's upper completion and a tubing hanger and safety valve are all on this string as it comes down. But this poses risk when you're running these inside the screens. You might have 1,000 or 1,500 feet of screen that you're running across, and then as you start entering the equipment in here, these are tight tolerances. You're opening up sliding side doors on the side. You're having fluid losses or possibly gains, and so a lot's happening as you're landing the tubing hanger. And you're in a situation you're kind of compromised because you have control lines across the tubing. You don't have your full well control capability. In fact, you might even have unshearables across the BOPs as all this is happening. So it's something you definitely want to risk assess. There's actually this whole issue here that was one of the reasons that client backed away from doing that, although I think it could be done. And the other concern is around reliability. You have this very, very complex system with all these connections and splices. It has a higher risk of failure, but once this is installed and you start production, you start getting some fines, from each of these zones settling up on top of these seals. Assuming you can get this installed, I doubt very much that you'd ever be able to recover it for repair. So if you had a failure, you either learn to live with that failure, or you have to replace the well in its entirety or sidetrack the well, and that's that obviously comes with cost as well. Not saying it can't be done, but to do a completion like this inside sand control is going to take a lot of thought, and there are some challenges landing it. But and technology is evolving to better enable this. Again, these downhole wet mates, if we can get those field proven in the next couple of years, could certainly make this a whole lot easier. One I'm just going to throw out here, because actually we're working on a similar problem right now for another client. They're looking at a gas field underlain by water, and they don't want to produce. It's going to be subsea, so it's similar to what your challenges are. They're going a slightly different direction. They're actually looking at these autonomous inflow control devices on their completion. There are no AICDs that are yet proven to be able to isolate water from gas, but there are two on the market right now that look like they're really, really close. Like, with some additional work could be made to work in this application. And I know of at least one operator who's actually going to partner with one of these two companies probably in the next few months to further develop this technology. This is drawn as an open hole horizontal gravel pack because that's how their wells are configured. But if you want to make this vertical, it would actually be easier to run. But you have isolation packers that isolate the zones. You have a solid base pipe screen, and you have these AICDs and sliding side doors that are run as part of the completion. The side doors are closed when you go into production mode. And basically, once you're producing, all the flow comes across the AICDs. Gas is allowed to enter the well, and as soon as water hits, it gets stopped. And so that way you can manage your water without having to run any interval control valves. It's an idea. And this is how at least one other operator is going to tackle their challenge, which sounds like it's similar to yours. It's going to change gears here and go into a few operational learnings and just kind of a few things you want to consider as you develop your system. This drawing here, you're going to see it a few times, but this is like the complete system. I've got the downhole completion here. I've got the tree in this area over here with some isolation valves around the tree, then the subsea control pod with the shuttle valves. The first thing I want to talk about here is thermally induced pressure gains in the lines. This is probably if you're going to run a hydraulic system, this will end up being one of your biggest design loads, very likely. And it's one that's actually unfortunately often ignored or not recognized by folks that are doing their intelligent completion designs. API 17D stipulates that these three valves, these tree isolation valves, are to remain closed when you're not actually opening or closing the ICV. This is provide a second barrier between the well, the production fluids and the environment. The first barrier is actually down the valve itself, and then there's the TIV, and after that it can go to C. Whenever this valve is closed, the downhole lines between the TIV and the valve are trap volume, just like our A annulus in the between the tubing and the casing. And just like the annulus, the line pressure will rise as the well warms, and the pressure in that line will drop as the well cools. And this can have some profound implications. I've got an example here from a well in the U.S. Gulf of Mexico. It was about 4,500 feet of water, about 25,000 foot deep well, and is filled with water-based control fluid, which is very common. Basically, when the well was when we first cycled the TIV open and closed, the gauges of the tree would have read about 2,200 psi, and this was on a cold well. If we then we close the TIV and start the well up and allow it to warm, the average line temperature rises about 86 degrees, and the pressure at those valves will increase from about 2,000 psi to a little over 12,000 psi. So we've picked up over 10,000 psi of pressure increase just due to warming of those lines. If this was a 10K tree, that could be very problematic for that tree, and also this pressure is acting on the valve itself downhole and potentially risking bursting the control chamber. So this is probably one of the most significant design loads you can have in the system. If I then open that valve once it's hot and allow that pressure to vent, it'll drop back down to about 2,200 psi. I'll dump about 0.6 gallons of fluid per line. If I then shut the well in and allow it to start cooling, my fluid in my lines will also start to cool and contract. It'll actually drop down to almost 0 psi, actually get down to quite a bit less than 1 psi. And we get down to the vapor pressure of the control fluid, and it'll continue to fall. So basically you can end up with several hundred feet of vapor in your control lines. And this could happen to you, in your extreme water depths, the same thing can occur. And if I then open up those TIV again, seawater will try and enter the control lines. It'll contaminate my control pod, and it'll contaminate my downhole lines. So this is a very, very impactful situation that you definitely want to work through here. Make sure this doesn't happen to you. And there are a few ways you can manage this. There are some modifications you can make to your subsea tree that I'll suggest here. The first one being to add what we refer to as a sea chest on the vent line from your downhole, from your ICVs. A sea chest is like an accumulator without any pressure in it, or just basically it's like a bladder or a balloon that will fill with control fluid under normal operations. If you then find yourself in that situation where you've opened the TIV and you've got a vacuum in here and fluid wants to enter the system, rather than pulling in seawater from the environment, it pulls fluid in from the sea chest, and that way you avoid contaminating your system. Another thing you want to add to your subsea system, if you can, to improve your operability of your intelligent completion, are flow meters. Definitely on the supply side, and I know at least one of the vendors really promotes these on the vent side, but these actually confirm that you have flow going to your ICVs when you're shifting them, and actually allow you to record the volume required for each shift over time, which can be a really important diagnostic tool. Another thing I'm a big fan of is what we refer to as an ROV logic plate for all of your ICVs. So basically you loop all your lines that are associated with your ICV system across this plate. So if you need to come in and do an intervention, say you want to do a hydro test on a line because you think it might be leaking, or you want to have an ROV come pull a vacuum on a line to mitigate a hydrate, or if heaven forbid one of these seals is leaked and now you have a risk of hydrocarbon going to the environment, you can have the ROV pop off this plate and do your intervention. And it's far easier to do this than it is to pull the control pod off the top of the tree, and far less risky. And my number one recommendation, which is something we've only been able to do in the past couple of years, is to add sensors to these lines between the TIV and the downhole valves. Previous revisions of API 17D, which is a governing document on subsea tree designs, did not allow us to do this. The current revision does allow us to do this. And if you haven't done this yet with your tree supplier, you want to get started on this because it is a difficult thing to do and they will fight you, but it can be done. And if you're, this is an incredibly powerful set of gauges that you can use to manage your well and also be able to prove that you have barrier integrity on these critical lines. Another lesson I'll share with you folks is around gas tight seals. I'm sure this has got relevance because you're developing gas fields. But again, these seals on the hydraulic control chamber are your primary barrier between the gas and the wellbore in the environment. If these seals leak, you can get gas up here. If it passes these seals, it can enter these control lines. And once it's in these control lines, the other barriers is TIV. And if it gets past that, it goes to C. Unfortunately, no vendor, so I'm not throwing rocks at any one vendor, they've all, I think, they're all in the same boat. They have never tested any of these, they've never tested these seals to be bubble tight. Whenever they've done any gas testing, there have been acceptable loss rates when testing. And if you're operating well like this, there is no acceptable loss rate. It has to be bubble tight. And I will say I did some testing on an ICV last April, and we did demonstrate that at least the seals we were looking at were gas tight, but they're also, in my opinion, probably the best seals in the industry. There are other seals out there that aren't nearly as good as the ones that we tested. So when you're looking at your ICVs for your application, spend a lot of time looking at these seals, ask about how they've been qualified, and understand their design and make sure you're happy with them for your application. Because there is a lot of evidence in industry that these seals are leaking on at least some wells around the world. I know Petrobras, for one, have had a lot of issues with these in some of their wells. Getting towards the end here, so I appreciate your patience. I got another slide here, again, because I think there's a good chance that you folks will be looking at some sort of electrically augmented ICV if you're going to be running more than 2 in your completions. And if you are, you're going to be relying on your electrical system, which is going to rely on these electrical wet mates. I've touched on these a couple times on the presentation. It's a very busy drawing. I apologize, but this is a drawing of a tubing, with the tubing hanger in red landed in the subsea tree. And basically all your cabling comes from downhole and it comes through the tubing hanger to this connector here. Then on the tree side, there's another connector that mates up with it that's operated by the ROV. After you land the hanger, the ROV basically drives these two together, and you have this connection takes place here. This is probably the least reliable electronic component in the entire subsea system. Again, Equinor quoting a 25% failure rate for this component across their portfolio in Norway. If you're relying on electrics for your ICVs and this fails, you lose everything basically. The designs for these connectors, the electrical feed-through systems vary, and so do the degree to which they've been qualified. Unfortunately, operators are terrible at sharing reliability data, so nobody really knows how well or not well these are operating in industry as a whole. They just know their own failure rates. I can tell you nobody's happy with them. We do know that onshore gas testing, the way we do our onshore gas testing, especially the way we bleed the pressure off, which can sometimes pose risk of explosive decompression, can pose risk to these. And also when we do our completion, one of the things we do before we run the upper completion is we pull a wear bushing, we expose this, then we jet on it to make sure everything's clean. That jetting action can be damaging to some of these connectors. So the bottom line here is you want to know your system's design, what poses risk to it, and how you can mitigate that risk. And if you haven't done this already, there are some industry groups, like one is CFOM, that are working across organizations. And actually, I find the dialogue that we have informally in CFOM is amazing between operators, where we're discussing our problems with these and how we can try and make them better. And as Gökhan mentioned earlier, there is an SPE paper out there. Some of the suggestions I've had on this presentation come from this paper, and there's a lot more information in there because my co-authors I think are they're phenomenal. Eric's from McDermott, one of the best guys on hydraulic fluids in the industry, and John and Rashid and Duani are each the product line champions for their for ICVs within their organizations. And we kind of got together and shared a lot of notes and recommendations. So I think it's a good paper if you're looking for further guidance around design and operability of an intelligent completion. Which gets me to my final slide. And again, I appreciate your patience. The biggest lesson learned from past projects is systems engineering, and with that, communication. Every intelligent completion is different, and we're always learning. And the one thing I can assure you is that these are never cut and paste completions. Even in fields where I've run 10 intelligent completions back to back, every one of them was different. These are complex systems that impact a lot of disciplines. We talked about completions and impact on drilling, like with casing design, subsea systems and operations. It's not just one person can do this. It needs to be a team of people working together to do this. And success in this requires a lot of work. And the operating company, which is you folks, need to manage and drive this. And the one thing I can tell you, which is unfortunate, but your service companies do not understand the system. They know their components really, really well, but to bring it together successfully and actually make a successful system is going to be up to you to do that. So with that, I'll shut this down and open it up to any questions or comments. And just one little final note there is you've got my contact details, and this isn't a one and done. If you have other questions in the future, you're free to reach out and ask me at any time. All righty. I'll stop sharing the screen here and open the floor.
Ron, thank you so much. I knew this was going to be good, but like I was holding my breath. This is so good. Thank you so much. I think there is a lot of good detail there, and I'm just thinking if I was a completions engineer working on Sakarya, I think you presented a lot of food for thought. I just want to see if anybody has any questions. You can unmute yourselves and you can ask questions. Eğer Türkçe soru sormak istiyorsanız Türkçe sorabilirsiniz. Ben İngilizce tercüme ederim. Or you can use the chat line. Same thing. You can ask it in Turkish or English, and I will try to translate it. And with that, I'm just watching and waiting. Any questions from our audience?
Yeah, I hope I didn't go too fast. I know it was a lot of information for 40 minutes. Oh, wow. A lot of questions.
Well, there's one here. You can see the chat line, Ron.
Yeah. All righty. Okay, question one, are there new technology that helped us close subsea BOP? Well, yeah, there are technology that can help you close subsea BOP in terms of shear capability. There's KBOS and explosive shearing capability, but to do something that's less dramatic, I mean, when you shear, you've just turned a small problem into a big one potentially. And in terms of being able to do like a ram closure around the control lines, I'm not aware of any technology that allow us to close like an annular around tubing and control lines and allow it to seal, so that that you do have ultimate well control with shear capability in most cases. But again, that's a big line to cross. Okay, and some completions breaking away from ICD.
Sorry, Ron. Before moving to the second question, I am working as the completion engineer in the Sakarya project.
Mm-hmm.
So I have a related question with the first question of Eren. So we were focusing on the running the upper completion with a chance of the closing the BOP. So we found some papers that the shape of the control lines and the design of the control lines can allow you to close the another BOP around these control lines. Did you hear, or did you have a chance to hear any of these designs, like the trapezoidal control lines?
I've not seen those.
Flat packs, did you hear anything about these from the companies?
No, in fact, what you're describing to me is news to me. I mean, we've done a lot of testing around control line, trying to get a seal, and I know we've played with some geometries, trying to play with the encapsulation shape. And to my knowledge, nobody succeeded in getting more than a few hundred psi pressure differential across that configuration. And especially in many of these cases, there's a lot of control lines that are running together, and just there's a lot, they just don't sit well together, and so we've really struggled to get a seal across control line. If you got papers, I'd love to see them. But I do know when I worked at Shell, and also well, especially at Shell, we did a lot of work on this, and I know some other operators, Hess is another one who did a lot of work on this, and ultimately were unsuccessful.
Yeah, okay. I will send the paper to you, because I think they succeeded to hold 1800 psi pressure around the control lines with the annular BOP. But actually, it cannot be verified as a well barrier. But it
Yeah.
helped for the operation, right? So yeah,
Oh,
I will
absolutely.
share. Maybe we can discuss further on the paper.
Absolutely. I appreciate that. Thank you.
Thank you.
So we can move on to the second question, Ron. You were just reading that.
All right. It's just saying some completions, perforations be away from the ICVs. Absolutely. If you run the ICVs with a lower completion, how do you get the data? There are different ways of doing this. You can do this. Oh, again, there's one design out there from Metrol where you can do this acoustically. It relies on batteries. But if you don't plan to cycle the ICVs that much over there, that frequently, the batteries can last surprisingly for a long, long time, and you can get low resolution data acoustically that way. Otherwise, you need to be cabled in there somehow, whether it's either part of the upper completion installation where it's run concentrically, or if it's actually in the lower completion, then you're looking at some sort of a wet mate that couples the signal across the upper and lower completion. There's inductive systems from Schlumberger, but they don't have a lot of power capability. And I think Baker have got they've had several successful runs with the conductive system. And I think Halliburton just installed their first conductive system in Brazil just a little bit ago. So those technologies are evolving for those downhole wet mates. Regarding the choke type valves, I'm not saying, well, yeah, it's, I guess I'm not saying, I'm not recommending that you don't run them, but you wouldn't want to make them your default valve because the choking system, it adds a lot of complexity, and complexity comes with a risk. And especially in a deep water completion, these are expensive wells, they're difficult to intervene on. And unless that risk is clearly offset by a reward, you don't want to, you don't want to do it. I know of one operator in the Gulf of Mexico that ran choking valves just because they felt they might need them late in the field life. Of the 10 that they ran, or sorry, 20 that they ran, 4 of them have got problems where they've spent far more money intervening on those wells and trying to get those choking valves to open properly, and they have yet to get any benefit from them. And and whereas an on-off valve would have had no problems at all. In fact, they did run some on-off valves in the field later, and they've been flawless. It's just the complexity, the challenges in getting them to reset. They've had a lot of problems. So again, if they add value to your field, absolutely run them, but just don't run them because you can. And if people who are
Ron, it's Kerem again. So it should be the well-known field, right? Because if you don't know the field, I think the cross-flow issue can happen with the on-off system. If you are fully aware of the production, maybe you can adjust the choke sizes or the flow area of the ICVs, and you can run the on-off system, right?
Well, no, yeah, I mean, crossflow can happen with the choking valve as well. And usually if you've got enough flow area on a choking valve to be able to make it commercial to produce, it has enough potential for crossflow as well. And I know like there's, it's just, but again, it's just the complexity. I mean, the principle of choking is great. It's just unfortunately the choking itself with a hydraulic system and those various little pistons that have to work, they don't always work flawlessly. And they're a lot more sensitive to debris and to any other issues in your subsea system that can cause problems. Like in the case of one operator, the tree system wasn't as clean as they thought it was going to be. They got some debris in the lines, and that's, I think, contributing to their problems, their choking system. But and they were so diligent, but unfortunately that's still stuck through the system. But choking can absolutely add value. I mean, if you're trying to manage water influxes or optimize production across zones, the value is there. Although I can also say there's a lot of operators that thought they're going to have choking, they're going to actively choke throughout the production profiles. And you go back, you talk to them later on, all the valves are, once they get to pressure equilibrium where they can commingle, they open both zones up wide open and they don't choke at all. So it's, again, sometimes, I'm not saying don't run them, but just make sure you've done your due diligence. Just make sure that all your assumptions of how they add value are correct. Does that make sense?
Yeah, absolutely. Thank you.
Okay. Yeah, because they absolutely can add value. There's no denying that. But I have seen them run where people just ran them because they could, and that was a mistake. Okay, another one here. Are there any redundancy for electrohydraulic ones? I'm not sure if I understand the question here. You basically, if with the electrohydraulic system, if they lose the control, the fluid in the electrohydraulic system, is that what we're asking about here? For
Hello,
Q4?
yes, yeah, that was my question. If you lose the electrohydraulic line fluid, so are there any backup system in the technology that then we can still continue operating the valve?
Yeah, they do have a reservoir there, so there is surplus fluid in the system. It's got a pressure compensated reservoir, so there can be a little bit of leakage, and they'll continue to operate. Although ultimately, if they do run out of fluid, like if you had a significant leak and they just lost their fluid, it would be inoperable as a remote valve. You can still get into all of these valves and operate them manually. There are profiles in the valve insert where you can stroke them up and down with a wireline tool, like a resolve tool from Schlumberger. But the electrohydraulic ones, that reserve is finite, and I'm not aware of any way where you could top it up if it were to leak. Does that answer the question?
Yeah, thank you.
Okay. And there's Q5. Yes, the slides, the MST systems are shown. MST is a selective side door system. It's not just Baker. There's Baker has one, but Halliburton and Superior, most of the vendors, I'm trying to think right now. I know I'm missing some. I think Schlumberger's got one as well. I believe. I've never run theirs, but and basically, if you're going to run a multi-zone ICV, I believe that you really are. It's going to be an MST type system because you need to have those sliding side doors on the wall like that, where you can, as you're running the concentric valves inside of there, you're opening up those side doors as opposed to trying to actuate a ball valve or something else like that. I myself have never run a multi-zone MST ICV into MST system, although I did all the engineering for the drawing I had in the Gulf. And we did risk assess it, but again, we did not run it. And I have actually been kind of talking to a number of my peers trying to see who has done this. And unfortunately, none of my friends I work with closely have done one inside sound control, although I'm still kind of reaching out to other colleagues. But it is, as I was saying, as you're in the, if you're going to run this system, the ICVs as part of the upper completion, which is the most reliable way to do it now, because that way you're not relying on wet mates. There is that risk as you're opening up those side doors and start having losses while you're still running your production packer and your upper completion, and also the tight tolerances. And if you get something stuck, you're in a very, very difficult situation at that point. And so, yeah, it's but again, I think it's about the only system that's really compatible with this technology. But there is always the risk of, I think the risk of gaining is pretty low if you've managed your well pressures properly, but losses are significant. But you can design it that when everything is landed, where you have seals that are engaged at the top of the system, and so you can prevent losses once everything is landed, and you could potentially even stagger seals through there. All that, I can talk more about this offline. That there's complexity that comes with that. But certainly you can have it configured that once you have everything landed, that the seals stop the losses. So that way you can set your production packer without losses on the backside. And if you want to talk about that more of that offline, we certainly can.
Yeah, that will be good for us because we will run these systems. I mean, we are evaluating to run these systems, so maybe it will help us.
Yeah, absolutely. No, it's sort of the holy grail what you're trying to do here. It's a very, very it's what a lot of other operators would like to do, and I'm confident it has been done. But again, I've risk assessed this a lot, so yeah, I'd be happy to sit down sometime. We can kind of walk through it, and I can show you at least some areas to look at in your designs, and especially if I'm not sure if you're tendering this this work coming up. You could include some language around this in your tender proposals and ask the vendors to come back and see how they would manage this. But I do believe that the sliding side door system is the way you want to go, like basically a single trip multi-zone frac assembly or gravel pack assembly is how you want to do this.
Yeah.
Okay, there's a example of the AICD. Okay, there's the magic, how it differentiates it. There's the methodology varies between the two suppliers we're looking at. One is purely a density system. They're actually using a 3D printed metallic kind of float ball that floats in different positions with according to the fluid density. And if it with very very low fluid density like gas, it's open, and as you have higher density with water, it closes. That's a very simplistic way of putting it, but they're basically purely using density. Another one is actually using a combination of density and rheology to differentiate between the two. One of them, they published some literature a little while ago in one of the SPE trade JPT some time ago. I can send you a link to that. And if there's any interest in this, I could talk to one of my clients who I've been involved in with this, and see and just make sure they're happy with me releasing names of these companies. But two of these systems technology I think look really, really promising. And again, that client is going to partner with one of these two companies, I think, in the near future to further develop this technology. But we actually were looking at some prototypes a little while ago, and they work. It's just a matter of scaling it. And yeah, okay, it's a good question. It's basically I'm suggesting a simple design first, then go to more complex options. But you have a complex field. It's yeah, basically where to start is a really, really good question. I mean, if you have a multi-layered reservoir, you need to be able to manage these reservoirs. You need a tool to do this. Otherwise, you're going to be increasing your well count, or incurring a lot of costs that really hammer your economics in other ways. So, I mean, there are a few options out there, and I think, but you may well be committing to a solution like the sand control, like we're talking about here, the multi-zone system, and that may be your most attractive option. And yeah, I don't know all the details of your field, so I can't say that explicitly. But I mean, with your complexities, all your layers, it doesn't sound like you can try and bundle multiple reservoirs across one ICV. That probably wouldn't be optimal. The AICDs may have some value for you. And that's actually not a really great answer, but I mean, the field economics are going to dictate what you have to do. And sometimes the only attractive option is the one that involves complexity. That's where all the savings are, and it's worth taking the risk. And it kind of goes back to a phrase we used at a client some years ago, where we talk about intelligent risk taking. You're taking risk, but you're doing it with your eyes wide open. You're doing everything you can to mitigate the risk, and you're doing it because the prize is so significant. If you're successful, that you have to try and go that route, and you may well be in that situation. You're good, great questions, by the way, everybody. I think these are very well considered questions. Hope my answers are up to it.
I thought that the answers were awesome, Ron. Just to kind of along the lines, I'm not a completions engineer, and I'm not offshore, in particular completions engineer, but I've tried lots of new technologies in my professional life, and simplicity and reliability in my mind trumps everything else.
Yeah, when you can, but sometimes, again, these environments, it's not always possible. As I say, I got kind of, again, going about the choking valves. If you don't need choking, don't run it, because simplicity is better, exactly to your point. But there will be some instances where the value proposition by introducing the complexity is worth incurring the risk. But again, you have the default position simplicity, and then if you have to migrate from there, then you do, but you do it very carefully and very in very measured steps. Oh, another question here. Okay, it's we're looking at basically there is really no installation cost variances other than the capital cost of the gauges, and you kind of touch on. I mean, by the time the procurement cost for a gauge system is negligible compared to the value the gauges bring to the party, and also all the other associated costs associated with installing them. And so whether I mean, the incremental cost of running the best gauges in the market versus the cheapest ones is maybe tens of thousands of dollars per sensor at the end of the day. And certainly I think it's worth upgrading and making sure you're getting quality electronics, because again, if you needed the data, especially in a subsea application, if they go dark, it's going to cost you tens of millions of dollars to replace it. So get good gauges. And it's not just electronics, it's the whole system, and understand the system and where the weaknesses are in the system. Every splice poses risk, and there's some designs out there that got far more wet, or what I refer to as dry mate connections, or potential leak paths than others. And these days I'm on a big hunt eliminating leak paths in the system because I've got confidence in electronics. What is the typical cost of ICV installation for 2-zone production? If you're looking at the incremental cost of the valves themselves and the feed through packers and the control lines and all that kind of stuff, to have an intelligent versus a not intelligent completion, it's going to be, again, it depends pressure ratings, what you're looking at, but you're going to be looking at several $1 million. I mean, realistically, I'm just trying to think right now for I should know this off the top of my head. I've just been doing a lot of cost updating for a client, and I could say 12.5K intelligent system, 2-zone. You're looking at an incremental cost somewhere in the order of about $5 to $6 million between rig time, which isn't significant. In fact, in some cases, the ICVs, because you have those valves down there, can actually make your installation easier through some phases. But there is quite a bit of incremental cost. That's for an on-off system, not a choking system. Not that there's the choking systems are slower to run, because that to go from closed to fully open can take you several hours. And sometimes you need to close the valve to do an operation, then you need to reopen it. And an on-off valve you can do in minutes. A choking system takes hours, and those hours are critical path rig time. But yeah, I'd say, just spitballing right now, I'd say roughly about $5 to $6 million is what you're looking for a 2-zone intelligent completion over an unintelligent completion, with everything else being the same tubing, same lower completions.
So we have one more question there.
The database. I have some data. I have some data. I've got to think about how much I can share. It's hard getting this because, again, even the vendors, even the operators, we don't, just as I talk about tree systems, the operators don't always get back to the vendors and state that they've had a failure, or if they do, they're talking to the wrong part of the vendor organization. It doesn't get back to the the main, like the product champions. And so the vendors don't know their own reliability. And I'm not saying that in a negative way. They just don't. And it's because in part, we don't give them the data they need to know that, and we don't hold them to it. But I do, and I know some valves better than others, I'll say that. But so I don't have a comprehensive database. I've got some data for a couple of the vendors I think is reasonably complete, but it's, the unfortunate thing is I don't think anybody has that data, which is really unfortunate. It's really kind of sad. We're talking about, things that are so impactful to our wells, and yet nobody in the industry actually knows how they perform. It is where it's unfortunate. It's just where we are as an industry, because we're so reluctant as operators to share this data across our peers, because somehow we think it has value, or it's embarrassing. I don't know, but it's just not out there.
Is CFOM useful, like for this particular question?
It wouldn't be useful so much for the ICVs, but around gauges and electronics reliability, and especially if you have any interest in fiber, CFOM has been amazing, because what I found there is you got Shell and Chevron and Exxon, and they're experts within their organization. Like Brian Seabrook at Exxon is a giant amongst fiber in the industry. And we have these operator-only meetings where the vendors aren't in the room, and the operators are talking and explaining what their plans are in the future and what problems they're seeing, and like Exxon almost never shares information. The openness of the dialogue, they're sharing their failures, they're asking if anyone else has seen this problem. I've been stunned by how transparent the dialogue has been in CFOAM. But CFOAM is less for ICVs, but definitely for gauges, because they address. It started mostly focused on optical and fiber optic, but there's definitely a lot of input there around electronics, and even Equinor talking about their 25% failure rate in their gauges. I about fell out of my chair when they started kind of going through explaining where they saw their failures, because no one shares that information these days, and yet Equinor they're showing it, warts and all, what's worked and what hasn't. So I found it tremendously beneficial being part of that organization.
So
and
that's
basically.
That's one good recommendation to TPAO, right? I think be a member of that group.
It's a great way, and especially I think I'm really excited by fiber. I'm working on a project right now where we intend to run fiber in 17 subsea completions in a couple of years' time, and to understand the challenges associated with fiber in a subsea application, it's been really, really helpful being part of CFOAM for that, especially. And I'm not sure whose subsea trees you're looking to run, because some suppliers are more advanced than others in terms of their readiness to run fiber. But I at first actually fought hard against fiber. I said that's just, again, to your point about simplicity, it's just one more thing to fail. But I also used to be a production engineer in my past. Now I saw the wealth of data you could get from fiber and how it could help you operate the well. I'm sold. It's the way to go. We have work to do to get there. And also, other than cost, there's very, very little risk to the well. It's just one more thing you strap on the tubing, and if it fails, you're no worse off than you would have been without it. But if it works, you're miles ahead. It's just incredible. Comprehensive comparison matrix. In terms of comparisons, I could tell you, I mean, there's actually there's 3 main suppliers. There's a 4th out there, Superior, actually run a fair number of valves in the Gulf of Mexico, but they're probably not a player at all in your part of the world. But yeah, I could, I'm not sure, what you're looking for comparisons, but in terms of, I could put some together quite quickly, because again, I talk to these guys all the time, and it's a good question, because I'm actually right on the process of tendering ICVs as well for a field. So I could put together something if you're looking. I'm not sure exactly what you're looking to compare, but I could, if you give me a list of what you're looking for, I could probably put something together quite quickly.
Yeah, so okay, Ron, this is gives, yes, to complement this question. We are actually in the process of, we tendered and we got the responses from the 3 main ones, and we're in the process of evaluating their proposals and then selecting the one.
Yeah, I mean, so I mean, what items are you looking to compare between the vendors? Like, what areas are you most interested in from their scope of supply?
Okay, yeah, actually what I will do then, I will get in contact with you, provide you more or less what we are looking at as a comparison matrix. We have some sort of matrices built. I'll share with you, discuss with you to see how we can rank that, right, to decide.
Sure, absolutely. Yeah, no, it's, and again, it's, I'd be happy to look at that. And again, I've got it, depending what it is you're looking for, I probably have some things I could probably supplement that with as well, possibly as well. But yeah, just reach out, we can chat.
Exactly. And then with time that I'm here. So you mentioned AICDs, right? So these were mainly for open hole applications, or you have seen them also in the case holder?
Our application is open hole. We think we may change our well design around, but there's absolutely nothing that would prevent you from running those in a cased hole completion. That drawing I had out there for open hole gravel pack could just as easily be run in a cased hole completion vertically. There's nothing. In fact, actually, it would be easier in a cased hole completion in some ways. You have to think about frac pressures. If you're intending to frac pack, just differential across the AICD would be something you need to manage. But certainly, if like a gravel packing application, like a circulating type pack, they'd be absolutely fine. I'd have to think about pressure for fracking, but in fact, actually, even they would be fine for frac packs. The SSDs are open, so you could do it in a frac pack application even if you wanted to.
Okay, and the result that you saw, they are working. Are they we're delivering, because this is selecting, I mean, sorry,
the timing's not going to work.
Water, right? Yeah.
Yeah, you know, what we saw are two kind of working prototypes. We're going to be doing a lot of flow loop work. We're going to pick one of these two to run with. There's a flow loop up in Norway. We're going to do a lot of flow loop work to further validate this. It's not field ready yet, but the principles are there, and we've seen working tools that actually can separate gas from water, which again, this has been a long time coming. And you know, there's work to be done, but you know, I really think that maybe 6 or 8, again, the timing probably doesn't work for your initial completions, but we're thinking, you know, 6 or 8 months of lab work, and we will have kind of, you know, tweak these enough to where in our application it'll work. And I think our application is probably going to be quite similar to yours, because it's a fairly dry gas. It's not super high pressure, so the density difference, I mean, because obviously pressure has an impact on density, but these are not high pressure gas wells, not particularly hot, so it's probably not unlike your application. And it's actually one of the more challenging ones for this type of system, though. And we, you know, again, there's two solutions out there that we've identified that look really, really promising, but they're not yet proven field ready technology. But there's operators that got a development in the Caribbean that if they, you know, if they cannot make this work, they don't have a field development, and if they can, then they do. And so obviously they're very committed to making this work.
Okay. Okay. Thank you.
Yeah, no worries.
Any other questions? Ron has been very kind to stick with us for close to an hour and a half here.
Oh, no worries. It's you know, it's.
You okay with time?
I'm fine with time. I got nowhere. I'm in no hurry, but I know it's getting late in Ankara as well. So it's just again, I appreciate the questions, because it actually suggested everybody was engaged in the conversation. So I didn't speak too fast, and I wasn't too mumbly, so that helps. So thank you for that.
That was awesome, Ron. Any other questions from TPAO side? You know, you have Ron's email address. Did you have your phone number in there, Ron, as well, or not?
I did not, but I'll I can. Well, I think you've got my phone number, don't you?
I think I do. So if anybody needs it, you know, just let me know, please. And Ron and I live about an hour's flight away from each other, so we're close to the same time zone. We're an hour difference. So if there's anything I can you know, expedite or help, I'm happy to do that. Ron, as you guys know, is an independent consultant, which in this case it really works for us, because he's not bound to any one single company where you can't reveal company secrets. So he is able to share his experiences with us. So you know, that I think is very fortunate. Yes, Steve, the presentation is taped, is recorded, and it will be posted on YouTube. And Ron, I don't know, do you if you want to send any copies of it or not, but I think this is available it will be available on YouTube. So the presentation.
Right. Sounds great. And I can yeah, and I'll go through this one more time, just make sure there's nothing sensitive in here. I don't think there is. I'll just do it one more time. I can convert it to a PDF, and I can send it to you as well. It may be easier for people to, and I'll add my phone number to it as well.
Okay, sounds good, Ron. If you do that, just send me an email, and I'll share the presentation with you as well. You know, you're welcome, Adil Bey. So, Ron, I think it's been long enough here, an hour and a half. Thank you so much. You guys, I didn't know when I contacted Ron. I'm not a completions engineer. I don't work deep, you know, subsea and so on. So I knew he was an expert. I didn't know how good he was. So that was just awesome, Ron. And
Thank you.
thank you so much. Very useful. And then based on the questions that we received, I think we have achieved our objective of, shedding some light or answering some questions for TPAO. And then any further questions they have, hopefully they can get in touch with you. So thank you so much, Ron, and we very much appreciate your contribution.
No, again, happy for the opportunity. And thank you for reaching out to me, Gökhan. It was good of you, and I just look forward to some further dialogue with everybody. Thank you.
Yes, it looks like it's coming. Don't worry.
Yeah, there we go. All right, everybody. We'll have a good evening over in Ankara, and we'll be in touch. Thank you.
Thank you so much.